All right, good evening, everyone. My name is Drew Desker. I'm the director here at the Kopernik Observatory. It's great to have a nice crowd here on a Friday evening for our Friday Night Live program. I also want to welcome those people that are watching on our live stream. Let's see here. I see a bunch of faces that are familiar to me, but not everyone. So who's here for the first time? Raise your hand. All right, good. A good number of people, all right. Okay, who here are a member of Kopernik? All right, almost the other half. All right, so so what I wanted to point out is that people who raise their hand second actually have a particularly important piece of knowledge and how valuable a Kopernik membership is. So we are a nonprofit, but we belong to an association called ASTC, Association of Science and Technology Centers. And this is a consortium of over 350 other science centers throughout the country, but even some are international as well. And all of those ASTC members recognize each other's membership cards. So for like a family membership might be $75 here. Down at the Franklin Institute, it might be $200 or $250, but you still get in to the Franklin Institute down there. So you could get into the Franklin Institute. You can actually get into the Roberson or the Ithaca Science Center, or MOST up in Syracuse, or the Intrepid down in New York City. So if you like this kind of place, and maybe this summer you might be doing some traveling, you might consider getting a membership. By way of background here, Kopernik has actually been a public observatory for almost 50 years. Next year we'll be celebrating our 50th year. And we'll be doing a bunch of special events. I even arranged for that solar eclipse to happen next year. And but what we're really trying to do here is promote lifelong learning. We have right now we're actually running our summer camps. We just finished our first week of summer camps here, STEM-based summer camps, and that'll go through the middle of August. But we also do a lot of school outreach. We have a thing called Kopernik Kids for kids that are from 3 to 6 years old on Saturdays once a month. So we'll be starting those back up here soon. And we do our Friday night programs. We're really trying to promote, again, lifelong learning, and it's an opportunity. It's not everything we do is always about astronomy. We've had people talk about the physics of music. Why does a violin, an oboe, and a trumpet all sound different playing the same note? We've had, actually, I'm a ham radio operator, so I've talked about ham radio and the technology that goes around that. But then we always bring subject matter experts in to talk about various things. There's actually somebody who grew up in this area that now is a flight controller down at the Johnson Space Flight Center. And so he zoomed in and talked about what it's like to be a flight controller for NASA. Tonight, we've got we're very fortunate to actually have one of the investigation team lead for the DART mission, which we'll talk about in just a brief moment. But again, every Friday night we'll be up here regardless. Next week we actually have a science fiction author that is actually, his name Nicholas Davis. He's spoken here before, but he's going to talk about, is there anybody out there? You know, the search for ET. So what? Again, sometimes the line between science fiction and science fact is just waiting for something to happen, waiting for time to happen. So next Friday we'll be doing that. I mentioned earlier that we do everything, we do live streams, and a little bit of background on that. So back in 2020, March of 2020, we had to shut down Kopernik because of the COVID pandemic, and we said, all right, fine, we'll just wait a couple of weeks for this thing to blow over. Didn't exactly happen that way, and so by about May, we decided, look, we still have all these speakers lined up, so let's start bringing them in. So we brought them in via Zoom to here. We then turned it right back around and pushed it back out onto our YouTube live stream. We now have over 13,000 subscribers on our YouTube channel. And not only do we do our Friday nights, but we also have done a number of other events. We get sort of a watch party. So if you might recall, a couple of years ago, when SpaceX launched their Crew Dragon for the first time, one of the two astronauts grew up 4 miles from here. It was Colonel Doug Hurley. So we actually did a sort of a watch party of his launch and ultimately their successful return. But also we've done a number of observing sessions actually Jeremy, who is running our live stream right now, has done tours of the moon and other night sky objects. We've also done eclipses. In fact, last May we had a wonderful lunar eclipse, and at one point we had over 25,000 people watching on at the same time. So anyway, I'm glad to have you here. Glad for those people that are watching on the live stream. When you are, as you have on the live stream, if you have your questions, put them in the chat. And we at the end of the presentation, Dr. Rivkin's presentation, he will entertain those questions. So let me get rid of my. Let's get. Come on. Here we go. There we go. And now, introducing Dr. Andrew Rivkin from the Applied Physics Laboratory at Johns Hopkins University.
All right. Thank you for having me. It's a pleasure to be here. Let me get my screen up. All right. And I don't want to show my whole screen. I just want to show this part of the screen. Sorry. There we go. This is what we want. So thank you. It's a pleasure to be here. And I'm going to be talking today about the Double Asteroid Redirection Test, which is this spacecraft that we smashed into an asteroid a little less than a year ago. So this starts with a bit of a hype video. Let me once again stop and make sure you're going to get the audio, because share sound, because this actually does come with audio. So hopefully, let's see how this works. So NASA made this not too long ago about kind of what we did.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the systems and see how effective that is.
This is a watershed moment for planetary defense and a watershed moment for humanity.
Okay, so that video is pretty cool for those of us who've been working on it. For people who have not been working on it, maybe it's less obvious what's going on. So the rest of the talk is going to be kind of explaining what's going on in that video, and then of course taking questions. So why do we do this in the first place? How often do we actually get hit by material or hit by asteroids? It turns out that in a sense, we are hit all the time. You have seen the Earth get hit by impacts. Something like 100 to 300 tons of material hits the Earth every day. Anytime you see a shooting star, that's what's going on. These impacts are very, very small, millimeter-sized pieces or less, or smaller, a gram or two of material. Most of it never reaches the ground. So that picture there on the right shows some telescopes in Chile. with the beautiful southern sky, and that streak over the leftmost telescope is a shooting star. It's an impact. These small impacts, obviously, we wouldn't have a whole program and send spacecraft to try to prevent or have programs to think about that because there are bigger ones. So in 1992, a little over 30 years ago, there was an asteroid that came in over the northeastern United States. This movie that will start in just a moment in the upper right was filmed in Pittsburgh, and it showed this fireball over the city. It was a Friday night, and a lot of people were out watching high school football, so they had their big, bulky 1992 era video cameras that were taking images, and so they were able to work backward and say, yeah, that thing that we just saw in the sky came from the asteroid belt. It was an asteroid. The largest piece that was recovered was in that lower right there. It's about a foot across, and it hit this poor girl's car actually in Peekskill. So New York State, a little bit further downstate in the Hudson Valley. But okay, so before it reached the Earth, it was probably about the size of the chair you're sitting in or the table you're sitting at, about a meter or two in size. So again, that's not really something we need to worry about. If your car is super unlucky, maybe it'll get totaled. But by and large, these are not the size of things we're worried about. About 10 years ago in Siberia, there was a larger impact. This was seen by dashboard cameras all around the area. It came in during the day. There was this big flash. People kind of rushed to the windows or rushed outside to see what it was. If you weren't at a window, maybe you didn't know what happened, but about a minute and a half later, you knew because there was a shock wave that went through the city that broke windows, threw people away from where they were, knocked them over. These school children were and their teacher were very surprised and not super psyched that this had happened. So this was caused by the impact or the airburst of a object about 25 meters in size. If you're not comfortable with the metric system, a meter is about a yard, so about 25 yards across, 75 feet. It hit in the winter in Siberia, so it was snowy and icy. The biggest piece hit a lake and punched that circular hole in the lake. Divers went down. They pulled out this piece here on the right that people are standing around. The angle is a little bit misleading. It's only about maybe a foot and a half across, and then in the middle there you see what smaller pieces of it look like. It landed in this area called Chelyabinsk. If you go on eBay, you can buy a piece of the Chelyabinsk meteorite if you like. But this was, again, more serious than just one person having a very unluckily parked car. This map here shows the straight line shows the track that this impactor had. The dots of different colors show where there was damage reported, where pieces were picked up. About 1,000 people were injured from this, all from breaking glass. Happily, no one was killed. So this, again, was about 10 years ago. Maybe you remember, maybe you don't. The largest impact that we've had in recorded history, we think, occurred also in Siberia. Siberia is big, and occurred a little over 100 years ago. This was something called the Tunguska event. There was a 12 megaton blast in this remote Siberian area. There were a few eyewitnesses. They were far away because if they were much closer, they wouldn't be around to tell the story. There were seismic signals. There were atmospheric signals that were detected around the world. The seismic earthquake signals were felt throughout Europe and Asia. The effect on the atmosphere was detected in Indonesia and North America. Because Russia and Siberia in 1915 wasn't an easy place to get to. World War I was going on, and then there was the Russian Revolution. Nobody got there to really check it out until the 1920s. What they found was this area where the forest was flattened. This kind of rough map compares the area that was flattened to Washington, D.C. I'm pretty close to here right now. And for those of you who are not familiar with Washington, D.C., each of the sides of the square here is 10 miles in length. So the distance from where you are to Binghamton is about half of that distance. And you can see this shaded area is where the forest was destroyed. Only recently have we figured out that this was an asteroid impact. When I was a kid and watching cable TV, there was a show called In Search of that Leonard Nimoy was the narrator for, and there was an episode on this explosion, the forest destruction. An impact was one idea, but there were a few others that were somewhat more outlandish. So this is thought to have been the largest impact in recorded history. It was something maybe twice the size of what came in Chelyabinsk, so something more like 50 meters across, 60 meters across, so 50 or 60 yards. And if you can imagine, comparing the area of destruction to the size of the impactor, you can see that it doesn't take something terribly big to cause a whole lot of havoc. And in fact, the Tunguska impact occurred on June 30th, which is why today is Asteroid Day. There's more than one holiday going on, in coming days. So happy Asteroid Day to everyone. I hope that you're, celebrating appropriately. I guess maybe coming to see this talk is your celebration. And from now on, you'll always know that June 30th is Asteroid Day. It's an official UN-sanctioned event.
Thanks for that very much.
The Tunguska impact occurred well before the space age. But U.S. satellites have been detecting smaller impacts since the late 80s. And so this shows every circle there is an impact of an asteroid of some size. Most of these are very small, but still large enough to show the big fireball in the atmosphere and burn up. This is Chelyabinsk here, like I said. It impacted again about 10 years ago, about a 20-meter object. The impact was the equivalent of 500 kilotons of TNT. That's a lot. And certainly the people of Chelyabinsk were fortunate that it exploded up in the atmosphere rather than making it all the way down to the ground. Of course, a big difference when you hear kilotons of TNT, that's often used to describe nuclear explosions. These are not radioactive or anything like that, so that also helps. So as these impacts have occurred, as people figured out, okay, Tunguska maybe was an impact of an asteroid, Chelyabinsk was clearly the impact of an asteroid. How often do these things happen? On the right there, we have a column that is objects that are 10 kilometers in size, about 6 miles across. So again, that would just about fit, I think, between where you are and Binghamton, but stretch most of the way. Objects that large are out there. The impact of an object about that size, we think, caused a mass extinction 65 or 66 million years ago that wiped out the dinosaurs. On average, we think they hit the Earth every 100 to 200 million years. And it's really bad when they hit. It's bad for everything living on Earth. Luckily, we know where all of the objects that size are that come near the Earth. There's only 4 of them. We know where they are. They are not a threat. We don't have to worry about that. If you go to the left, one column, you get to objects that are 1 kilometer in size. So I think that's a little over a half a mile across. That size was of great interest. Congress tasked NASA to find all of the objects that are about that size about 10 or 15 years ago, and NASA then asked, funded a lot of studies to find them, a lot of telescopes. And so we think we've basically found those 2. Those would be really bad if they hit, not as bad as the dinosaur killers. But we think those hit every 500,000 years or so. Again, we think there's about, well, not again. We think there's about 900 to 1,000 of them. We think we found them we think we're in good shape there. If we go all the way to the left, to the far left, every year we get hit by something about 4 meters in size, about 4 yards, 15, 16 feet across. These, have one of these bright flashes like I showed in the videos. Maybe something will land on the ground that you can pick up. There are 500 million of them out there, we think, that are that size or larger. We've discovered very, very few of them, but again, that's okay because they really don't do any damage unless your car is parked where maybe it's unlucky. So then these next two columns are where we're going to focus here. That 25-meter column, that's about the size of the Chelyabinsk impactor, that could cause an air burst, that could cause injuries if it's over a populated place. There's a lot of those. We found very, very few for that size. We really just want to know that they're coming in. If we find them, we want to be able to say, okay, look, there's going to be a flash over your city. You can watch it, but then get away from the windows, get away from the chance for broken glass. And then that middle column is a size that's big enough that it can cause enough damage that we want to actually try to stop them if we can. About 160 meters across, so about 500 feet or so. These hit the Earth once every 25,000 years. There's about 20,000 of them out there. So once every 25,000 years isn't bad. The odds are good that we are not going to have to deal with that in our lifetime, but we have only found about half of them or fewer. So until we find more of them, until we have a much better handle on where they are and know that there aren't any coming our way, there's an effort in parallel with the searches to prepare just in case, to make sure that if we did find one that was going to hit in 20 or 30 years or something, that maybe we could stop it and just prevent the problem entirely. So there are different techniques that can be used to deflect an asteroid, depending on the size of the asteroid and depending on the amount of warning time you have. This just kind of shows the ones that we think are just about ready. Maybe some of them need to be tested, some of them don't. Here on the y-axis, this again has the diameter of the asteroid, and on the x-axis is the warning time. Chelyabinsk falls in this kind of civil defense region. So even if we found that something that size was going to hit the Earth in 30 years or 50 years, it wouldn't be worth the expense and the effort to go and try and do something about it. The smaller the asteroid, the more of them there are. And the more of them there are, the more often they hit the Earth. So this KI, kinetic impactor technique, is suitable for these kind of smaller, more frequent asteroids, and that's why the community has been interested in testing them. And the kinetic impactor technique is very easy. You take your spacecraft, you ram it into the asteroid you're worried about, and by ramming it in and adding the momentum of the asteroid to the momentum adding the momentum of the spacecraft to the momentum of the asteroid, you change the asteroid's orbit. And now instead of it being at the same place at the same time as the Earth, it arrives early or it arrives late. So this is a simple physics problem in some ways, but there are nuances that make it less of just something you can calculate on paper. We didn't know how much momentum would be transferred from the spacecraft to the asteroid, and particularly we didn't know how much debris would be made from the impact. All of that debris is going to carry its own momentum, and it's going to change the detailed answer. So we wanted to have a test flight. Now, if you look at the animation there on the right, the Earth is moving around the sun, the asteroid is moving around the sun. They're both moving around the sun at about 30 kilometers a second, which is about 20 miles a second. We want to change the speed of the asteroid when we hit it by only an inch a second, a fraction of an inch a second, of millimeters a second. because we don't want to smash it into a million pieces. We want to keep it in one piece and just move it. So that means to do this experiment, we need to measure the difference between something moving at 20 miles an hour, or 20 miles a second, and something moving at 20 miles plus 1 inch a second. And that's a hard measurement to make if you don't have two spacecraft. And we wanted to try to do this as cost effectively as possible. So my colleague, Andy Chang, at the Applied Physics Lab, came up with a clever approach that you only need one spacecraft for. And that is to go to an asteroid that has a moon. About 15% of asteroids have moons. The moons are just like other asteroids. They just go around other asteroids. There's a big asteroid, a small asteroid, like in this animation here on the right. So this is a radar, based on radar data of a real asteroid binary system. And while the two of them together go around the sun at 20 miles an hour, 20 miles a second, the moon goes around the main body more like 6 inches a second, or 4 inches a second, or 8 inches a second. So you can make that measurement much, much easier. There are other advantages, which I'll get to in a little bit in the talk. But basically, the lowest cost way to do this, the most cost-effective way to do this experiment, is to hit the moon of a binary asteroid. And that is what we've done. So this shows kind of a summary of the DART impact. We launched in November of 2021 from Vandenberg Space Force Base in California. We impacted the asteroid moon Dimorphos on September 26th of last year. Dimorphos is orbiting the larger moon Didymos. It was going around in 11.92 hours, so every 11.92 hours it would make its whole way around. The DART spacecraft was carrying a CubeSat that the Italian Space Agency made. And then the whole thing, after LiCiCube passed by, the rest of the results were measured from Earth-based telescopes and a few telescopes in space. The asteroids that we're talking about here are very small compared to a lot of celestial phenomena and celestial bodies that are out there. You know, if you're thinking about Jupiter or a mission visiting Jupiter, Jupiter is gigantic. The sun is gigantic. These galaxies are made up of billions of stars, so they're yet more gigantic. Didymos and Dimorphos, small. They're human scale in a lot of ways. Dimorphos, our target, is about the size of one of the pyramids of Giza. Didymos, which Dimorphos is orbiting again, isn't really its axis length is really about the same as some of the tallest skyscrapers. And then DART itself is pretty small. DART is, I'll show some pictures momentarily, but DART is about the size of a vending machine, not counting the solar panels. And then when you count the solar panels, those go out so that it's about the length of a bus. This shows the spacecraft. We only had one instrument. That's this camera called Draco, which is a descendant of a camera that is on board the mission that went to Pluto, the New Horizons mission. Some of the other technologies that were important for us, there's smart navigation. That's our autonomous navigation system, because we were coming in at 14,000 miles an hour and trying to hit something the size of one of the pyramids of Giza, so we weren't sitting there with a joystick. That had to be figured out on board. I mentioned LiCiCube. I'll mention LiCiCube again, the CubeSat donated by the Italian Space Agency. And then the solar arrays roll up or they started out rolled up, which saved space. There were 4 things DART needed to do to be considered a success by NASA. We needed to impact Dimorphos last fall. We needed to change the orbit period from 11 hours and 55 minutes. We needed to change it by at least 73 seconds. which we calculated was the smallest amount that we could measure. We needed to measure that period change to a 7.3 second precision. And then we needed to measure what we call beta. It's the way that the momentum change in Dimorphos relates to the momentum that the DART spacecraft had. Here are some pictures of DART getting put together. You'll notice that this is May 2020. So just like we were hearing from Drew about how the challenges that that Kopernik faced when COVID began, we had similar challenges. In pre-COVID times, this room would be filled with many more people, much closer together. So building the spacecraft, there had to be adaptations. Everyone would be wearing masks and these clean suits anyway, but there was a lot of use of Zoom, of cameras, so people who might normally have been in the room and engineers checking up and doing tests would instead be looking at home on their screens as people would hold their camera phones up to various parts. And at this point, this is very early. It doesn't look that different from a vending machine. There are cables, there are structures, but it's just a box at this point in the process of being built. Here's the solar array being inspected. You can see some of it still rolled up here, and kind of rolling out. Here's just after the Italian CubeSat was placed on the side, and that it is literally it there on the side with two very happy Italian engineers. Here you can see the solar panel rolled up behind the engineer on the right. This shows what the spacecraft looks like as a whole, and it's basically the size of a person when the solar panels are rolled up. So this is what we sent to impact Dimorphos and change its orbit. We literally put it on a truck, and literally it was driven from Maryland to California. It took 2 or 3 days. They only stopped to change drivers so that they could kind of roll through the night like a 70s movie. And there were 2 or 3 cars full of a support crew just in case anything happened, kind of trying to keep up. Here it is getting put inside of its fairing. They could have fit a much larger spacecraft in there, but for us it was just DART alone. Last look before it got closed up and put on top of this SpaceX Falcon 9 rocket. You can see the rocket is a little bit beat up. I think this is the first time NASA used a pre-owned, pre-loved rocket for one of its launches. And then the launch was pretty spectacular. It was the first launch I've ever seen. And it was a beautiful, beautiful night launch. Just amazing to see. So we launched when we did because it was the time to do so, to get to reach Didymos when we wanted to. This is looking down kind of at an angle from the North Pole of the solar system. So Earth's orbit is that inner oval. DART is kind of making its way out to Didymos and Dimorphos, which are on that outer oval. I'm not a huge basketball fan, but I think it could be argued whether this was a block or a charge. You can see DART kind of gets into position, and Dimorphos and Didymos come charging in. So it would have been a technical foul, I suppose, but DART wasn't around to shoot the shot. Here's what it looked like in the last hours before impact. On the left, you kind of see 1 pixel, and that's what it looked like to DART even 4 hours out, just this 1 pixel. At 4 hours out, the engineers were satisfied that SmartNav had found Didymos, and so could make its own way there. So from 4 hours, it was steering itself. At 68 minutes out is where that second panel is. maybe you can see Didymos is a little bit extended. It's about 8 pixels across. Dimorphos is there. It's only 2 pixels across. And that is the point at which SmartNav found Dimorphos, and again was the engineers were satisfied that it found Dimorphos, and so DART was told, okay, stop tracking the big one, go to the smaller one. That third panel shows what it looks like just 2.5 minutes before impact. Dimorphos is still not very big. It's clearly not a dot anymore. It's about 38 pixels across. This is the last image that has all of Didymos, which is making its way out the corner of the image there as we got closer and closer. And then that fourth panel shows the last complete image, which was taken about a little less than 2 seconds before impact. I don't know how big the room is there in Vestal, but I suspect certainly those rocks near the center could fit in that room pretty easily. And the whole scene is only about 30 yards across, so maybe that's a little big for that room, but you could get a lot of that central part of that image right there in that room with you there.
Yeah, our room is maybe about half that size.
Okay. Right. So this, whoops, doesn't look like, let me start this video over again. So this shows the last 5.5 minutes sped up by a factor of 10, except then the last 6 images are going to be shown at real time. They were coming in 1 per second. So again, coming on in, Didymos is making its way out the corner. With 2 minutes to go, SmartNav was told to just coast because the engineers figured it would, calculated that the odds of it helping were about the same as the odds of it hurting. So these final images came in. We were all watching from our various spots, saw this partial image, and the crowd went wild. And the crowd online also went wild, which was fun to see. Although we were too busy at the moment to kind of catch up on this, but we did catch up with it later. So here's the kind of view of Didymos and Dimorphos to scale, about, again, 2.5 minutes out. These are oriented correctly. The way that we on the team think about this is that here, Didymos on the right kind of looks a bit like a fish, and it's got this kind of fish lip pointing out there. And then it's chasing Dimorphos. Dimorphos here on the left, you can kind of see, again, maybe a nose or maybe it's a lip, and you can see the little fish tail. So the big fish is chasing the little fish to the left. We were able to use the images of Dimorphos. We wanted to get as accurate a volume as we could. We need as accurate a size as we can get to make our calculations as accurate as we can. And something that we use a kind of a bit of a trick that's maybe familiar to a lot of you. So this is what the images look like of Dimorphos. This is what we saw. This is what you'll see on Wikipedia, or if you go to our website. And Didymos itself is off to the right in this image. And so sunlight from Didymos, reflected off of Didymos, came back and was illuminating that unlit part of Dimorphos, just like you can sometimes see the unlit part of the moon at some phases lit by Earthshine. So if you stretch this image and you increase, mess with the contrast, you can maybe see that there are details to the left of this bright piece that was looking like it was just all by itself. And if you trim away the glare, you can see that Dimorphos is a lot bigger than you might have guessed from just the image alone. If the unstretched images, if you think this is the edge. So DART hit this area. We needed to come up with names for the area it hit, because otherwise we wouldn't know how to call it. So we proposed and got approved that the names for places and rocks and craters, if we find any, on Dimorphos are named after percussion musical instruments. So it hit in between Atabaki and Bauran, near Kakavela. Those are not coincidentally A, B, and C. Start with A, B, and C. This is again a close-up view of that central area where DART hit, and if we put a we know enough to know where exactly it hit. This is an outline of the spacecraft, and these rocks here are about 6.5 meters long, so 20-ish feet long, and rise 2 meters or so, 6.5, 7 feet above the surface. And so our crack team went and were able to make animations showing, what hit where. We think that solar panel on the left first hit that rock. I guess I'm sorry, not on the left. The one on the right, in the right panel, and also to the right in the left panel, hit this rock first. Then the other solar panel grazed that rock, and then the main body hit Dimorphos. This all happened within microseconds. So as far as the spacecraft was concerned, it was instantaneous. But as far as the impact modelers are concerned, and I'll get to their slides shortly, what hit exactly when could matter a little bit. So DART hit, and DART was done. But the CubeSat was deployed 2 weeks ahead of time, and its job was to document as much of this as it could. So this CubeSat is about the size of a cereal box, so it's smaller still. It had 2 cameras, a color camera called Luke, which had a little bit lower spatial resolution, and a monochrome camera called Leia. They're Star Wars fans in Italy, apparently, which had a little bit better spatial resolution. And it made its closest flyby to Dimorphos about 3 minutes after DART did. So it was released, kind of backed off, and then took images. And here's what it saw. The time until impact is up there in the upper left, and then you can see that Dimorphos got bright. Here, the main body here you see is Didymos. There's a little out of focus thing to the lower right, and it will flash, and then still be bright, but get a little bit fainter. So that's what the Leia camera saw. The Luke camera was in focus and was able to get some better data. This, instead of showing time until impact, shows distance to close approach, and you see this splotch to the lower right and Didymos in the upper left, and then it swings around, and now that Dimorphos and that splotch is in the lower left. So what's going on here is Dimorphos hit, it threw out a lot of debris, and the debris was in the shape of a cone. As we approach, you're coming toward the cone, and then after closest approach, you're going away, and the cone is pointed away from you. So that's what's going on in these images. There was a lot of debris, and the LiCiCube images have been invaluable for figuring out, a lot of the details. This image we've been kind of, informally calling the Spider-Man image possibly for obvious reasons. This is one single image from LiCiCube, and each larger box has stretched the contrast of the box, the smaller box, by a factor of 2. So that's done to show these fine details. The two, what you're seeing here is Didymos on the lower right, and Dimorphos and the ejecta on the upper left. And you can see these beautiful filaments and rays of debris coming out that we can follow for quite some distance. The distance between the center of Dimorphos and the center of Didymos is about 1 kilometer, a little more than half a mile. So these rays are stretching out for miles in many directions. And LiCiCube passed by, and then, like I said, we had telescopes on the Earth and in space that then took over. We had telescopes on literally all 7 continents that were taking part, as well as the Hubble telescope, JWST, and the Lucy spacecraft happened to be nearby, and they were willing to take some shots too. The impact occurred when Didymos was overhead in the Indian Ocean, kind of near Reunion. So a lot of our most powerful telescopes on Earth are in Chile, in Hawaii, here in the Canary Islands. So they didn't get an immediate view. Instead, it was telescopes in Kenya and Reunion and South Africa and parts of the Middle East that got the ringside seat. And here's what they saw. These pictures and this animation or movie on the right come from a telescope in South Africa. And what you're seeing is at the moment of impact, the Didymos, I'll back up slightly if you're not used to this sort of thing. There are stars, and the telescope is tracking at the rate of Didymos. So Didymos is moving relative to the stars, but because they're centering Didymos, it's making the stars look like they're moving. At the point of impact, at the time of impact, there's this huge increase in brightness from Didymos and Dimorphos, and this wave of material moves off. In this movie, moves off to the right. And this was unexpected. We're still working out exactly how much of this is dust, how much of it is that we vaporized the surface of Dimorphos. So this is still actively something we're working on, but it was very exciting. And like I said, unexpected. Here I'm showing a couple of screenshots from the Slack space that the DART, the DART team was using. And you can see very quickly, we impacted at 7:14 p.m. Eastern time. So here were the messages going then. Here someone took a screenshot and was showing it, and hey, we hit, amazing. And then people were, I guess, very impatient, and you can see any visuals yet from ground-based telescopes. And 3 minutes later, 7:17, we got the news that we got this video, and Kenya and South Africa were saying it was brighter within 2 or 3 minutes. So it was definite instant gratification for us that we weren't expecting. Like I said, there were telescopes around the world on all 7 continents that were taking part. This shows that they all took data. We didn't just make a list and sign them up. That we used all of their data in the analyses that I'm going to be talking about here. And as I said, we also had data from Hubble and JWST. Didymos was the first object that both space telescopes looked at simultaneously. And the JWST folks in particular just did an amazing job because Didymos was moving across the sky relative to the stars much, much faster than they were spec'd to do. So they really, really did a great effort. There's some structure in here that is due to the telescopes. Here in Hubble, you can see a cross pattern, and in JWST, you can kind of see a 6-pointed star. But other than that, everything else is real and is debris coming out of the system, and you can track and spot some patterns in both that are present in both of these space telescopes. Both the images from both space telescopes. We've had already some publications come out about the Hubble data. We're working on the JWST data, and of course, we're trying to track features and track debris if we can from the LiCHA-Cube data to Hubble and JWST and beyond. This movie, hopefully it's working, shows the JWST data over the weeks following impact and what it looks like. So this is now a much wider scale, and this is thousands of miles long, this tail. So you can see this initial brightening and this material streaming out, and the development, although the Hubble wasn't tracking perfectly all the time, so some of it's cut off, but this development of this tail as small material got swept back by the solar wind, just like what happens in comets. So within a couple of days, it had developed this tail. And this movie was made from New Zealand, not the Hubble Space Telescope. They had They have a much smaller telescope. They have much worse weather than they have at Hubble. I guess at Hubble there's no air. I guess it's hard to get worse than that, though. So this is every night that they observed. They averaged all of the images. So that's why you see these streaks. These are stars moving and being averaged out. And here too, you can see the development of this tail. I'll let it start again. You kind of start with these kind of horns almost going upward into the lower left, and then those go away as that material is swept backward into this tail. This is the pretty picture part of the presentation here. This is from one of the largest telescopes in the world in Chile. This is kind of the equivalent of the Hubble movie, except so it shows these things common among all of these telescopes: the debris coming out, the development of this ejectocone, and then that material getting swept backward into a tail. And the tail stuck around. This is from 52 days after the impact, taken from Arizona. Again, it's just this beautiful long tail that goes thousands and thousands of miles in length. I think it's certainly reached tens of thousands of miles in length. Here's an image from New Mexico. Again, Christmas Eve. Folks wanted to get to the telescope. Folks were eager, even on Christmas Day. Even on Christmas Day, to observe. The tail is still around. Here it is in February. It's fainter, but you can still see it in a movie. By March, you would even the larger telescopes were having to average all of their pictures to get it. But here it is, 168 days later. There's still a tail. The persistence of the tail surprised us. The tail is still there today. I'll tell you that, because we have Hubble time. They're still looking. They still found it. So this is really interesting to me. None of us, again, we could see the numbers on the page, but really internalizing what that meant was not necessarily so obvious. Dimorphos itself, I said the pyramids of Egypt. Here's the vehicle assembly building at the Kennedy Space Center. Maybe some of you have been. Dimorphos is also about as big as that building. Even if you haven't been to that building, you can see the sizes of the cars here. So it's a building. It's a human. It's not crazy to imagine how big that is. In December, the tail stretched, like I said, tens of thousands of miles. It stretched most of the way around the Earth in December, and it's only gotten longer, even if it's also gotten thinner because the material gets stretched out. And the amount of material in that tail, we think, is about as much as would fill 60 railroad cars. So you've all seen railroad cars. Imagine those filled with sand and gravel. And 60 of them, so a long train, but not a crazy long train, probably not the longest train you've ever seen. All of that made those kinds of images and movies that I was just showing. So all of this is cool, but none of this is what I said. There were 4 things NASA wanted to get for us to be considered a success, and all that was not one of them. So to do the real work part of this, we needed to measure the period change of Dimorphos, and the way we did that was by using a technique called light curve measurement. Didymos and Dimorphos are only ever seen as a single point of light in our telescopes. They're too close together and too far away to be seen as separate, except by radar, which I'll get to in a moment. So we can measure the brightness of that point of light go up and down as Dimorphos moves into Didymos' shadow and casts its own shadow on Dimorphos. So hopefully you can see the animation there as Dimorphos going around, moving into shadow, and then this trace here showing how the brightness dips every time it does that. So we made measurements like that before the impact, very precisely figured out the state of things before we went and messed it up. We went back to the telescope, and all of these measurements that showed this beautiful tail, a lot of them were done to try to make this measurement and just happened to also get the tail. And it just shows that this shows the real data. Real data is messier than nice animations. But what we found were dips that corresponded to orbit periods of 11 hours and 23 minutes or so, rather than the old orbit period. So these two are blow-ups, close-ups of the data along the top. We did this for many days. This is only about 10 days worth of data, but we did that for months. to come out with the period change, which is about 32 to 33 minutes. I think it's 1990 seconds. We also took radar data, like I said. Radar data are a bit difficult to explain, but basically the distance down from the top is range, and the distance left and right is frequency. So like when you hear a fire truck coming your way, the sound changes pitch as it approaches versus when it's leaving you. The same thing is true when you send radar to detect an object. This side is moving away. This side is moving toward. So this is what Didymos looks like spinning away when detected by radar. Dimorphos is really in one spot. It's not. It doesn't have this Doppler shift, as we call it, so much. There's where Dimorphos is. We can do the same trick and say, here's where Dimorphos would have been if we hadn't perturbed its orbit. Here's where it is. So this is how much we change its orbit by. And this number agrees with the other technique, the light curve technique. So we wanted to measure beta, this measure of how the ejecta, of how the momentum imparted to Dimorphos compared to the momentum we brought. If there were no ejecta, it would be, we would not change Dimorphos's orbit very much. And then depending on how much ejecta we made and how much momentum that carried away, we might make it move faster. So using these unscientific terms, we changed Dimorphos's orbit by more than some and less than lots. This momentum enhancement factor, as we called it, was 3.6. So we brought in some amount of momentum, and Dimorphos's momentum changed by 3.6 times that much. The ejecta took more momentum away than DART did. The ejecta did most of the work. We're doing impact models. We've turned over, all the data we have, so that the people who do simulations like this can figure out what the surface of Dimorphos is like. They're doing their best to match the ejecta and the Lichicube data. So on the left is that Lichicube movie I showed, processed a bit so that instead of changing distance, everything appears to be the same distance. And then on the right there shows these impact models into Dimorphos, what they have right now. And by placing boulders and things on the surface, they can get a decent match to that ejecta pattern. We have shape models of Dimorphos again, and we've been able to put specific boulders on the surface to match as well as we can what we think the surface is like, so that these impact models can go forward. We've been publishing everything we can, open access, so that taxpayers like you can read our results if you care to. In April, we published our most recent results in Nature, and these 5 papers related to DART and the DART impact all came out. Then the first 4 were by team members. The last one was by a group who were not affiliated with the team, but had their own private telescopes, and they did citizen science. There are lots of terms for citizen science. I think it's also called, local science, things like that. So this was done by people in Africa who had these telescopes, and also were able to get some great science out of it. So of these requirements, we can check off. We hit in last fall. We changed the period by as much as we needed to. We have measured beta. We have measured the period to the required precision. We haven't quite gotten it written up and published yet, but that's why we've got it soon there. So we're in excellent shape with that. It's on a personal note, this has just been an amazing experience. I've been involved with DART since the start. Here I am, with my colleague Nancy Chabot standing in the room with DART. Here's a group of us at the launch, getting to see the launch, getting to see it move across the sky, in images that people took on its way out. It's been wonderful to see how interested the media has been, how interested the public has been, and to get to do this. So it's been really, really gratifying to do this. And we have this amazing international team. We have telescopes on 7 continents. We have scientists from 6 continents who are involved, and really just because, like I showed earlier, impacts can happen anywhere. Impacts can hit anywhere. So it's fitting that people around the world are helping each other tackle this problem. There is a mission that is going to follow up DART that's going to launch next year, that the European Space Agency is going to launch. It's going back to the Didymos system. It's going to make some measurements that we could not make because we were a one-way trip. And a lot of those mission team members have been working on the DART team, and we hope to also be working with them. In the meantime, the DART project ends September 30th. Is our scheduled end date. We will continue to be working and analyzing data until then. I'm sure team members who have other support, who are funded by other means, will also continue to certainly do analysis, and the data will be public so people can work on it. We'll continue to have a presence until then. We have an outreach page that will certainly be active until then, where you can get 3D printable model instructions for printing the Didymos Dimorphos system or DART on your 3D printers, where you can have instructions to build toy brick models, and this augmented reality experience. So in closing, DART has really been a great success. We moved, as in that first video, we moved a celestial object for the first time. We changed its orbit on purpose for the first time. We demonstrated that this kinetic impactor approach is a viable technique to potentially defend the Earth if necessary. This isn't an operational, we check the box, we can do this anytime we want, but it shows how we would do that. It shows that would be something we could do. The large period change shows that the ejecta carried much more momentum than DART brought in, and so it was more effective than the minimum case. And so that means, in principle, that we could use this on a larger object than we thought, or at a later time than we thought. And with that, I will happily take any questions. Thank you for listening, and thank you for your interest. And happy Asteroid Day.
Well, thank you very much. This was just outstanding. We've got a nice crowd here. I know for sure we've got questions on the YouTube chat, but do I have any questions here locally before we go to the YouTube chat? Anyone? Or how about, I'll start in the YouTube chat, and then maybe that'll bring up some other ones. So let's see here. Andrew asks, what's the smallest size asteroid we would attempt to use an impactor for, assuming we had enough warning?
Yeah, good question. So it is probably going to be something about the size of maybe about 100 meters, maybe a little smaller, maybe a little larger. I think the part of the potential issue is that it's hard to move small ones. They're very easy to disrupt and break into a million pieces. At the small end, maybe you don't really care, but those studies haven't really quite been done. On the other hand, it also costs money to go and deflect something, and it's not clear whether it would be cheaper to just say, okay, we'll replace every window in town. At some size, it's cheaper to replace every window in town than it is to launch the mission. Having said that, it'll probably depend also on where it's going to hit. If something 40 meters in size or 50 meters in size is going to hit the ocean, and they say it's going to hit the ocean, it's not big enough to have a tsunami, we probably would let it go. If it was going to hit, Manhattan, or it was going to hit, if it was going to hit Beijing, I'm sure the Chinese would have something to say about it, and they would want to do something. So it's hard to give a cut and dry answer, but it's probably around 50 years.
Interesting. And also, you said that the ejecta actually had a larger effect on this than so that your calculations arguably would change, and I would imagine also the size of the impactor. Would, can you just throw more lead on there or whatever, just to add more mass?
Yeah. The beta, the amount of ejecta, was within the range of predictions. So there is that, but it was much above the minimum case. We had to plan for the minimum case because that was going to be the hardest to measure. And yeah, when there are conferences that people go to and they do these exercises and they say, okay, what if something's coming in? How do we approach it? And the strategy that people seem to like, rather than saying, okay, we're going to make a bigger and a bigger and a bigger spacecraft, to give it a bigger and a bigger and a bigger push, is to send 2 or 3 or 4 when they game it out and say, we'll just keep hitting it, we'll keep tapping it until we get what we want. And then when we're done, when we have what we want, if we have too many, we'll just have those miss.
Right.
People want to hedge in case something blows up on a launch pad or fails in flight.
Sure. Let's see here. We have another question from the chat. Actually, a comment. I don't know. This is a question. So there's another holiday called National Near Miss Day on March 23rd, commemorating the day in 1989 when an asteroid came within 500,000 miles, about two times the distance to the Earth. How do you know the size of that asteroid? Or do we know the size of it? Do you know of that asteroid, and do we have a sense of its size?
It's not ringing a bell, which doesn't mean that which maybe means I need to go look it up. Usually, when we're measuring asteroid sizes, ideally, there are lots of ways to do it, but the way that we're kind of often left with is just saying we can measure the brightness. We know about how reflective these things are on average. On average, they reflect 15% of the light that hits them. So if we measure the brightness, we say, okay, it's probably about this big. The ones we can get more data for, we can get much more precise answers. But usually these things that we found them last week, they pass close, and you hear about them on TV or read about them on the internet, and they say, well, it's between 2 and 5 meters or something. It's usually just based on that brightness and a rough.
All right. Though it seems to me like now they're talking about comparing it to the size of giraffes. I don't know what that's all about.
Oh, yeah. Okay, I do. I think there's one particular columnist out there who likes kind of comparing the sizes of these things to animals, to saying that this asteroid is the size of 50 penguins laid end to end or something. And they're just trying to engage their readers. But it's I think there's a when we say something is the size, it's this maybe I'll go back and find that find the slide in here that I'm thinking of, measuring something. We like to measure things by length,
right.
But asteroids really are volumes.
Right.
So this columnist likes to use the lengths.
All right. I did a fair amount of time in Boston, and at one point they measured one of the bridges across the Charles River in Smoots. Apparently there was
in Smoots, yes.
Yeah, there's an engineering student that went to MIT, and his name is Smoot. And one evening, he and his buddies measured the distance across this thing in how many smoots it went across. So I guess it depends, smoots, giraffes, whatever you want to call it.
Just to finish the thought, it's like in this one, right? So Didymos is this big, this Burj Khalifa skyscraper is this big, but Didymos is much, much, much bigger because it's a sphere that size.
Right.
So people want to say, well, this skyscraper is bigger, but it's just kind of how we use the language. It's a little funny.
Let's see here. There was another question in the chat from Doug. What were the masses and velocities of DART and Dimorphos when they collided?
DART was about 500 kilograms. And Didymos is about 5 billion kilograms. So it was, so Dimorphos is 10 million times more massive than DART.
Right. Excellent. Okay, very good. Any questions here? Oh, now we got some questions here. I'm going to run back here.
My question is, are there other darts in case something unexpectedly pops up? And are there backup darts so that if you miss, that you have other ones to fire off?
So first, I will reassure folks that there is nothing incoming. We know of nothing coming our way. We built DART, as you saw, we started putting the pieces together in 2020, in spring of 2020, and we launched it in fall of 2021. So we don't have, if we were to find something, and we were to want to use this technique, we would need a few years of warning. People have been discussing, in fact, this week we even had a workshop to discuss this. Does it make sense to design things and keep them in storage, or does it make sense to design things and put them in space just in case, or do you want to build them as needed? I think the community priority certainly is to make sure that we continue the searches so that we know what's out there and we have as much warning time as we can. But one of the things that came up, for instance, was the idea that you would build something and keep it in storage just in case, and maybe after 20 years you'd use it, or you'd get a new one. And I don't know, thinking about the state of things in 2003, and just how far phones and computers and other things have come, I don't know if we had built something in 2003 and needed to use it now, would we have said, okay, well, that's very nice, but we can do something much better now. So it's a funny balance that we're working out.
Okay, very good. Any other questions here? We got another one in the back.
Hello. Do you know what sort of material Didymos is made of? And a side question to that, depending on what it is, would that change the amount of ejecta coming out of it to change the speed?
Great question. We do have a very good sense of what Didymos and Dimorphos are made of, and it turns out that they're very, very similar to the kind of rock that hit Chelyabinsk. We can remotely measure. We have techniques for remotely measuring composition that we've calibrated using rocks like that on Earth, meteorites that have fallen to Earth, and so we think it's this type of material called ordinary chondrite, which is very, very common. It's the most common asteroid material out there. We think the amount of ejecta probably depends on the strength of the rock and the strength of the surface. We think that very weak material would give us more ejecta. So, you can imagine if you have clods of dirt that crush very easily, that you get more debris than if you had something like a hard piece of granite. But if you remember what the pictures look like, that the surface is very, very gravelly. So we're not sure if that is what is mostly mostly causing that result, whether it's that it's the rock strength or it's just that it doesn't matter what kind of rock it is. If it's powdery or gravelly, you're still going to get the same thing. That's still research we're doing.
All right. Any other questions? Yes.
Do we have a sense for how much this entire project cost?
We do. It's something like $330 million, 350, 300, somewhere in that range, spent over 5 or 6 years. So it's, well, I guess that it's whatever that is, $1 per person in the U.S., I guess. It's, well, there you go. That's the answer.
There you go. All right. I have a question. What you say you're the mission lead? What was your job, or what were your jobs as part of this mission?
Sure. So I am, I guess, still investigation team lead. So basically, this mission was a planetary defense mission. It was not a basic science mission. So, so the missions that the rovers on Mars or something going to Saturn, would have a science team. So we didn't have a science team. We had an investigation team. So I was in charge of that, along with my colleague Andy Chang. And our job was basically to make sure that the data that was being taken was sufficient so that we could do the analyses we needed to do to make the mission a success. So to make sure that the telescopes were lined up to take the data that we needed, that the camera on board was going to be able to take images up until the very end and be able to take images that weren't washed out or weren't too dark or weren't too grainy, to say the equivalent. To make sure that the Italian CubeSat was interfaced correctly so that it would work, so that it would be able to take data. So that was kind of my day-to-day job there. And now it's making sure that all of these results get written up and published so that people can see what we did.
And build on it. Great. Let's see. I noticed, again, you showed that map of the world and all the various telescopes that have done some observing. Did you actually have to? Because my understanding is that any of these, research telescopes, you have to put in a proposal for time on that telescope. So did you have to do that for every one of those scopes?
Well, we did not for all of them. We did for some of them. We put in a proposal for HST, for instance, and got, convinced them that it was worth doing.
HST is Hubble Space Telescope.
Yep. There were telescopes in Hawaii. Oh, I'm sorry. Yes, the Hubble Space Telescope. There were telescopes in Hawaii that we had to do that. But actually, let me see if I can get that slide up again. Some telescopes are just different. Almost there. No, went too far. Some of these telescopes are just different in that they are operated by universities. So then all you need to do is convince the university. We had a contract with a couple of these. So we had Lowell Observatory on contract. So we used their telescope. Some of all of the ones that have LCOGT with them, which is South Africa, Australia, Texas, Hawaii. I guess there's not one in Hawaii. But we also had a contract with them. There's one in Chile. Some of these other ones, the VLT in Chile, we had proposals. We got all 4 of the telescopes up there via proposal. And then some of them, like here in Massachusetts, that was a private amateur astronomer who has a lot of experience doing these sorts of measurements. And he said, all right, I'm going to do this, and donated his time. This one in Qatar, at Qatar University, I think, it was a student run observatory, and they just took their time and did it. So it was a combination of things, from writing proposals to just having people who are interested and willing to donate their time and time and effort.
Okay. Where was this built? Was this built at Hopkins, or was okay? So that clean room, that image in the clean room is something you have at Hopkins.
Yeah, that's at the Applied Physics Lab,
Yes.
which is part of Hopkins. Different parts were built elsewhere. The solar panels were built, I think, in Washington State, and some of the propulsion was built elsewhere, and then they were assembled in Maryland. I mean, right, the CubeSat was built in Italy and was shipped over. So pieces were built in various places, but most of it was constructed in Maryland, and then it was all put together in Maryland.
Now, as I recall, anytime you're putting a spacecraft into orbit or into space, you need to sort of really give it a good shake and bake. And I'm wondering, is that something facilities you have there at Hopkins, or did you take it like to Goddard or whatever?
Yeah, we have facilities at APL. We've built, although Goddard also has, and depending on the availability of the different places, sometimes we have to go there. We've actually built a lot of spacecraft at APL, both civilian and military. So the spacecraft that went past Pluto, the New Horizons spacecraft, we built. The Messenger spacecraft, which went to Mercury, we built. Near Shoemaker, which went to asteroids around the turn of the century, we built, and then numerous instruments on other spacecraft. So we have facilities like Goddard and JPL do.
Very cool. Very cool. Any other questions here? Okay. Here we go.
How much time would it take to make another spacecraft if there was an emergency?
It depends on how big of an emergency, and how much how much money people want to throw at it. Again, we were just kind of talking about this week, so this is a very timely question. Depending on it, it might be that it would be going to some company or the National Weather Service or whomever, and saying, this weather satellite that you were thinking you wanted to launch in 3 months, what if we took it instead? So it might be kind of commandeering something or taking something partially built and then adapting it rather than really building it from scratch. Would probably be in a real emergency what would happen.
All right, very good. Well, I can't thank you enough for taking your time. This was just an outstanding presentation, and thank you for the work that you do, and you and your colleagues. And if by any chance you ever made it up to upstate New York, we'd love to show you our little observatory. And speaking of which, even though the haze is the smoke haze is certainly affecting us, Alan, we got something to see out there? Okay, Venus is a little low in the sky, but the moon's still out there. So we have a rule here that you cannot leave Kopernik until you look through a scope. So I'd like your keys until that happens. And so again, Dr. Rivkin, thank you again for your time. Happy Asteroid Day to you and your colleagues, and have a great weekend.
Thanks for having us.
Have a good evening.